Okay, then we'll get into part 3, which is your floating and your fixed, okay, fasteners. All right. All right, so when we say we're dealing with the floating fasteners, you have like a 2 or more parts, right? And they gotta be joined together in your assembly or manufacturing, yeah. And you will use a fastener to join them together. Your fasteners are your bolts and then your nuts, right, going into the bolts. So all these parts they have clearance holes, okay. So clearance holes it's just like allowance, right? We call the clearance like allowance, how much you can vary in that, yeah, tolerance defined for these holes. So clearance hole they always have it, and that relationship between the fasteners and the parts, right, being held together, we call that the floating fastener, yeah. So okay, so when we have the fastener diameters are all the same size, and then your clearance holes, they also have the same for all fasteners, that we can be able to calculate it mathematically, yeah? So what we want to try to find is the clearance holes and the fasteners diameters all together. We consider that, and first thing we want is T, and that's your tolerance, yeah, to be applied to each part. What do? We do the same thing. Get your maximum, yeah, material condition hole size, and then minus your maximum material condition fastener diameter out of it. Okay, so then you are going to get the tolerance to be applied to that each part. So let's take a look at it in the diagram. So let's take a look at the value. So we're going to calculate the position tolerances, and we call for the floating fasteners when they are all together. Yeah. So here is your hole diameter, which is this one. MMC again is the smallest hole. Yeah. So 0.390, and then your bolt diameter, which is from here to here. Your hole diameter is from here all the way to here. And you're going to minus that, and you're going to get the position tolerance, which is this guy, yeah, it's going to be 0.15, yeah. You have, of course, your bolt is going to go into here, and then you have your nut, yeah, is screwing right here to keep that bolt in that position in this hole, okay. All right, now we have series. So right here you have mating parts, yeah, we have all kinds of 1, 2, 3, so bolts right here, and then you have 3 nuts to hold them, yeah. So you can be able to get your T, and then your H, and then your F here. So that's your tolerance of the hole max, and then this one is your fastener, yeah, diameter. Fastener diameter, you can see it visually. Your hole diameter, you can see it. You minus the fastener diameter from the hole, you're gonna left with your tolerance, yeah, again and again the same thing. And we're going to calculate that, and here is another formula. This one is for the fixed fastener. So when your parts are being fastened together, yeah, one of the part is threaded, so the bolt or your stud is going to be restrained, and that condition we call a fixed fastener case. Meaning like your fastener, in this case the bolt is fixed, yeah, to the part. So if it is desirable, we're going to get the same thing, tolerance, we're going to calculate it. This time you're going to minus it, and then we're going to divide it by 2, yeah, for the fixed, because one of them is threaded. Alright, so we will take it down to half for the floating, of course. So here we go, we put it, yeah, and here is your thread, so thread it into the hole right there. So in order for us to get the tolerance in between them, yeah, all you have to do is divide it by 2, so the original space is now reduced half, yeah. Why? Because your fixed fastener is now threaded, meaning like screw in straight into the material, yeah, tighter, meaning like you're losing the space. So when you take a look at it, yeah, so therefore the tolerance space is going down half. And of course, after calculating, you're gonna have the value right now without the value. So anyways, for these tap holes, you're gonna get the tolerance, which is going to be calculated this way, and you can see it in your feature control frame in that little box, yeah, one row table. Okay, projected tolerance zone, we're going to use the position tolerancing for the projected tolerance zone. So let's take a look at it. Alright, so if we have like a threaded fasteners or press fit pins, yeah, stud, press fit mean like you're just pushing that pin into that hole, okay? It's kind of like a studding to make it, like strengthen that connection or joining, mating. So the part will stay in the position that we fastened or threaded together, Of course, if you have like environmental wear and tear, of course they can come out, yeah, but you definitely do maintenance to check all these pins and the fasteners are properly positioning and staying where you put it in, okay, in manufacturing machines. Why do we have to do it? Because it's so important for function, yeah, of that design or the assembly, because they have to do what they're supposed to be doing. Since we join them all together, that got to stay. The function got to stay intact, and so it's really important, yeah, to control the perpendicularity because they're fitting to each other usually at 90 degrees. So the perpendicularity of that feature axis got to be in that space adjacent to that feature surface. Yeah. So let's take a look at it. So we go into here in the very first example of your projected tolerance zone. So you can see right here your tab holes are right there located. Yeah, their position is right here. The true position is given to you with your datum, which is your C and D and E right here on these appropriate and sorry, I gotta come back into here. I think I forgot to tell you about the interference. Yeah, so in order for us to avoid the interference that can happen because of the orientation, interference is completely dealing with the orientation of your fixed fastener, and to avoid the interference, you have to do the tolerance, all right, projected tolerance to make sure it's controlled by your inclination of the hole into what it is supposed to be assembled. Yeah. So now we'll get into the example number 1 where you can be able to see the no projected tolerance zone. So your parts with the holes are going to do with the press fit pins. Yeah. And or your tab holes that's going to serve for your poses or stud in your design. And of course, they're all located with your position tolerance because position tolerance is completely telling you where they're going to be, okay, on that part. So it's really important the location of each one of them. And projected tolerance zone is important because we don't want that interference, yeah, in the assemble mating between these mating parts. Interferences, we call it noise, by the way, okay, meaning like there is something that doesn't belong is there, and we don't want the intrusion, okay, of the other. We want this mating to be as functional as it should be, okay. So we got to make sure all the tolerance are projected so that they fit well, yeah, to each other. Okay, so here I come back to here. Here is your feature control frame, giving you the position tolerance of 0.01, and then we have a thread node right there, major diameter 0.5, and you have 2 of them. Yeah, so that's a 2 times, giving you with a 13 number of threads right there, and we're doing a course, right, for this part. So that's your UNC. So this is your thread node. So if you need to review, go back to MAT 101 to review that. And here is your identification of your internal or external thread, okay, A and B. And then let's go. So our strategy is to come up with the projected tolerance zone, yeah. And your feature control, of course, it at max, which is this little m is telling you your maximum material condition. So your cylindrical tolerance, we're gonna put it into this view, okay, which is here, yeah. We're seeing a site and also here. So now we're gonna look at this, right, from the side view, so you can be able to see the cylinder very clearly. So your cylindrical tolerance is 0.10. I already gave it to you. Yeah, that's in inches, because by looking at how your decimal is writing without the 0 in front of your decimal, we know that decimal point, we know that we're in the British, yeah, or English system for the unit. So make sure when you design it, make sure you're in inches. And I'm going to extend only to the size limits of that part. Okay. All right, now we are coming into here, your center right there for the axis. So here you can see there's no projected tolerance zone, yeah? And two of them still identified with this note. And here is your red zone right there, yeah? So that's your tolerance zone. And of course, you still have your major diameter in there, yeah? It's gonna aim at the extent of the limits of the part, limits of the size of that part, okay? And here, this little yellow line is showing you it's a worst case scenario because it's not aligned with where is the perfect position where the axis is supposed to be, but it's kind of like going diagonally in that hole. But that's okay, but it's just the worst position that you account for, so you won't make errors more than that, and your errors is going to be included in your tolerance. So that's the best practice to do it so far. So the worst possible orientation is this little diagonal yellow line right there, okay, in this example. So your feature axis orientation is going to be anywhere within that zone, okay? So now let's go to look at this next slide. Here we can see like how this, right, before, look at that, this is a perfect, yeah? And now we have orientation, meaning like your direction changes. It was 90, now there's an angle. So now look at that, yours is move, along that axis line. They have to parallel to each other. So therefore, see how it deviated from the true position like that, yeah? Of course, now let's get into the mating parts and see. So now we bring in the mating part. So here is the mating part and here is your part, and they have to go into each other. So you have your mating part at this, we're at the maximum material condition, and we're considering the worst possible circumstance permitted by that tolerance range, leaning to that side, which is your right side. So we're gonna see the consequences if we don't do the projected tolerance zone, what's gonna happen by joining in this method without the projected tolerance zone. So when you look at it and we're gonna put that in, see that the bolt is like completely going into inclined direction like that. So that's a huge error for it. So if you think about the aeroplane having this type of mating is going to bring the entire plane down. Yeah, why? Because the environmental forces can be able to threaten this misaligned joining. So they carefully check every fastener and fit. And if they found like this, then you're going to restart everything again, okay? So it's really important. So there are planes that go down, right? And you don't really need to pay a lot of money for the terrorists to bring in the guns and things like that through the airport. If you take out about 5 screws from the airplane, it's going to come back down right in there for that amount of distance that it's going to be flying. So you can see the airplane route, okay? They are carefully calculated, to be able to withstand those type of mistakes that the environmental terrorists are calculated. So that you have to get like not only like the direct flight. Direct flights are okay, but then also very risky. And for direct flight, the airplane companies, they gonna use the best flight they ever got. That's why you have to pay more money for those kind of flight, because we use the age, all right, airplanes for the airplane with 1 or 2 stop, so one airplane is going to fly about 2 hours and then going to stop. So why? Because they calculated if this type of mistake going to happen on the wing, somewhere, the environmental wear and tear or mischief, somebody trying to tamper with that, we can be able to solve that kind of issue by flying the shortest distance and giving you 1 or 2 stop. So that way they can check, all right, all of this fastener in that rest time, yeah, all over this. Every time the plane stop, maintenance is going to come in and scan everything, yeah, take a look at if everything is okay. If the maintenance team is bad, then they're not going to do their job as usual, lazy, then worst thing can happen, yeah. Whatever that is, shorter distance is a better flight, safer flight, because we think about all of this, yeah. And a longer flight, of course, we will use the state-of-the-art planes so that this kind of mistake cannot happen, yeah. So anyway, so let's go back to here. This is an example of if we don't use the project tolerance zone, things can go wrong like that, yeah? So there's a reasonable possibility that this interference, the noise, right, gonna happen. Noise means things that not supposed to be there is there, yeah, which is like not best fit for this joining type. Because the assembly got to perfectly, at least got to be fit with the accepted or allowed tolerance, yeah. All right, so let's get into number 2, and we will do the projected tolerance zone, and let's see how it goes. Because the projected tolerance zone is going to extend, yeah, from your datum feature or your surface away from the part to a minimum distance indicated. So either in the feature control frame or specified dimension on the drawing. And how we do this projected tolerance zone from your datum surface or datum feature, yeah, is that we take the minimum distance. So let's see here. So in this example, we're using the projected tolerance zone of 0.010 inch, yeah, diameter, of course, for this one, cylinder. So you can see in this view, your datum is C. You also have a secondary and tertiary datum. In other views, not in this view, you can see it, yeah. So that's going to extend a minimum. Here is your key point right there. A minimum about 1.25 inches, all right? And that is indicated right here. Like P for the projected and 1.25, we're going to have a projected tolerance zone, okay, for this original tolerance zone, which is 0.010 in there, okay? So when the feature is, of course, at your MMC. So that is a 1.25, that's a minimum inches from your surface, yeah? Surface meaning here. Because we're still dealing with the diameter of 0.010, okay? All right, now we'll get into the zone. So that zone, we have an MMC right there, don't forget it. We're gonna point that down, and that's your axis, all right? That's our plane that we study with our coordinates, yeah, planes right there, so you can see the center of that axis. And of course, this is your depth and the hole are right in there. Of course, you have two of them going on with the this is thread node, yeah, and thread node is going to tell you everything about it, the depth, right, and your thread numbers, your internal, external, everything in it. So here, you can be able to see, yes, the 0.010 inch positional tolerance zone, okay, is the blue little one right there. Then we're gonna have a very worst case scenario, yeah, how this tolerance is being jeopardized like that. So it's gonna go off of our regular axis, your true position axis, and then look at this, yeah, the angle or orientation changes. So right now, we're gonna take our projected, because projected minimum is allowed, is about like a 1.25 in this example, yeah. So we're gonna project it out. So let's go back to one slide up, yeah, here. So now here, yeah, so we're gonna project it out, the minimum 1.25 up. So that's your tap hole, and we're gonna adjust that, yeah, to show the adjust to show that worst case orientation, so we can see, yeah, because of this zone, then we can see like how off that is, yeah. So now let's go into the next slide. And here we get into assembly. So you have your mating parts right there, and you try to align it, but then there's an error, yeah, because it's off of the true position. Now go into there, and you're gonna put your bolt right into the hole. So that's your hardware assembly, and you don't have interference because we account for this distance in there, okay? So meaning like we're accounting the tolerance up to that level, yeah? instead of only up to the surface in the first example without the projected tolerance zone. Now our tolerance zone is now projected all the way up to meet this head of that bolt. Yeah, so we cover here and here. See that? This distance got to be minimum, otherwise your bolt is not going to fit right into that hole. Yeah, so that's why the minimum distance got to be in there. Yes, in this case the minimum length is 1.25, and of course it's nothing happened because the bolt is still in this hole. Yeah, don't think like because of this exaggerated drawing here, don't think like it's that much off. Yeah, outside you can see the difference of it. When you look at it, you're gonna think like the bolt is right in the hole. Yeah, perfectly in. It always looks perfect, but you have to scan it to see the interior stuff. Yeah, or measure the vibrations and the temperature. Anyway. Okay, then we will get into the alternate method for identifying your projected tolerance zone. How are we going to identify that? So it depends on the mating. So now we have axis, true axis here for this part. Of course, here is your cylinder, here is your control frame giving you 0.2, yeah, 0.2, so we're in matrix. We have two of that hole right there. We're still in position tolerance, and we have a projected, but we have to determine the value of it, yeah? So our job here is to identify your projected tolerance zone. So we know that the projected tolerance zone is going to be right above that surface, yeah, datum surface. So here, and we usually take the minimum. So in this case, it's 24, yeah, minimum. And we're going to use a heavy chain line. With heavy mean thick, yeah, thicker line. So here, look at the axis. Your axis is kind of like a thinner line in your drawing, and we're going to give it application drawing or hand drawn. You have to give a really, really thick line for that, yeah? So it's going to show you the height of that projected tolerance zone, yeah, from that surface. All right, now, so here is your true position, and here is your mistake or error, yeah, machining error. So the axis is going to change orientation that way. Of course, your true part is right here, yeah, your hole is right there, but then we need the projected, yeah, tolerance zone, which is 24 millimeter. In this case, it is millimeter because you see the 0 right in front of the decimal point. Yeah. So if you have a 0 right in front of the decimal point, we are in millimeter unit system. Then we'll get into here. And here is your datum. Yeah, that's your datum C, which is your primary datum with the 3 points contact, yeah, between these two surfaces. And then your mating part, yeah, is going to be shown here with this, yeah, see that, to show the worst case scenario alignment, right? The alignment is completely off, yeah. And here is our regular tolerance zone, and then we're going to apply the projected tolerance zone, which is your P 24 millimeters, yeah, in there. So right now the mating part is shown with the worst possible error you will ever make, yeah, with this horrible alignment. But the part assembly is successful without the interference because of this little projected tolerance zone defined in it. So every time we define and put a value in it, your machining, the way that we machine, got to be very careful, yeah, and we have to understand that our machining got to be in that zone, okay, which is 24 millimeter. I'm going to go back one slide up here, yeah, so don't forget 24 millimeter, yeah. So that's a lot, 24 millimeter of that height, minimum height. And that is going to make sure that that bolt is going to stay in that misaligned hole right in there, yeah? Okay. So what do we do about that is we come to make sure that the assembly is supported with the right amount of force, yeah? Depends on these material type, yeah? We have to think about all of this. Fasteners got to be reliable, yeah, to make sure that the mating parts are together, fastened together. All right, now we will get into the review. And what is this? I don't know. Oh, okay. So this is just the first slide. So you will have to go to the next slide to see the picture. Okay, so now we have the picture that you can be able to see for our review. So when we think about the position tolerance, yeah, and we have fixed fastener like your bolts, your stud, your press fit pin, you've got to consider the projected tolerance zone because it's important. Yeah. So because if you don't use that projected tolerance, there is a interference can happen in that type of mating. Yeah. Why do we need the projected tolerance is to give the extended control. Yeah, because this little control can't do it, because look at that, how like far away from our tolerance zone right here. Yeah, it's like this much of height is far away. It's got to be minimum because you got head of that bolt. If you take the maximum of it, it's gonna even kick this bolt out of it. Yeah, so the mating surface height got to be up to there. Yeah, up to this misaligned height, of course. So you have to have that type of projected tolerance zone, so the control is not only on the feature of this part, but also we're gonna have a control over the mating part. Yeah, so in that way we can be able to reduce or eliminate the interference. Yeah, interference is just a noise. Okay, so we have the two parts that got to be assembled together. And of course, we will always, consider the projected tolerance zone to find it and apply it. So in that way, we can be able to reduce the interference, between these parts. So very good for the manufacturing. This type of practice is the best practice, one of the best practices. Okay, so let's get into coaxial feature on the position tolerances. So coaxial, every time you see the co, meaning like you're dealing with the multiple features. Yeah. So therefore you have a coincident axis sharing the common axis. So your coaxial, you can control it by using the tolerances of your position, your Reynolds, your concentricity. Yeah. These are all the tolerances that's going to control your coaxiality. So out of that three, your position tolerance is the least expensive. So since it is the least expensive method, we're going to use it all the time. So it's most applicable. Yeah. All right. Okay, so let's take a look at our very first position where we are dealing with. Yeah. And here is your control frame right there. Your unit system is in matrix because you see the 0 in front of the decimal. I'm saying this again and again. You should be able to get it by now. And your diameter for the head is 19.5, and it has a zone which is going to go all the way to 20.5. So the width is going to be 0.5. Yeah. And then of course you do have another diameter for this. Yeah. That is going to be 11.8 all the way to 12.0. And your control frame is right here. Your datum surface is going to be right here, R, and we are at the maximum material condition, not your RFS. So let's get into this section view so we can be able to see, look at that. So this is just your gauge, trying to verify this values for these tolerance. So your virtual condition, your VC of your dimension, and we're going to use it, and that is going to be your perfect, right? So therefore your gauge, and we will use this gauge to investigate that position tolerance. So let's go into here, and of course this is, you can see how the bolt, the fastener is going to go into this hole, and you can see the part, and you have your perfect coaxiality sharing the same axis, between your head and then your shank. Here this is your shank of that bolt, and of course they both are at MMC. So your datum is at MMC, which is right here. This surface inside, and then your tolerance for diameter tolerance is 0.4. Again, don't forget the diameter tolerance is not for the size of the diameter, again the position of this hole. Okay, so your datum feature is at MMC. Your control feature right here is also at MMC. So now let's go into here and look at this little blue line right there. See that? So that's a little tiny 0.2, radius offset from that zone, which is your perfect position, which is your perfect I would say like the axis, yeah, for sharing. This axis is coaxial because it's shared between this head and then this chunk. And that usually happen, yeah, that's little offset happen because you're dealing with the both maximum material condition for both part. So now your size, yeah, here 20.4, 19.5, and then here is going to be 12, yeah, for your diameter of the shank, and then of course the diameter of your head. And then of course this little one is going to be 0.45 radial offset because the, yeah, from here to here is a 0.9, from here to here is 19.5, altogether is 20.4. So that 0.45 is your radial offset. Radial offset means it's just outward, okay, outward from this axis. So it's a little bit of distance coming out of that axis, true position axis. Okay. Then we will come after the head. We're gonna come into this chunk, yeah, on this side of the part. And here we have another offset. One is 0.1 and the other one, okay, but right here, see, and that's 0.55. Yeah, it's like 0.1 off from this side, okay. Okay, so when you have your datum feature and then your control feature are at LMC, yeah, we have a total of 0.55, yeah, I already showed that to you, maximum radial offset. That is going to coming out of your true position between the two axes, because your two axes is coaxial to each other, yeah. But then again, you still have the offset. And why do we have the offset like that? Even though this is the same hole, it looking like that, is because of this material on that part. Even though we drill it, machining can never be 100% perfect. Yeah, so even though we design it that way, give you the specification, dimension of that, when you actually drill that, yeah, by physically, yeah, on that part, you will never get what is specified on your drawing or on the paper, yeah. So what's on the paper cannot be done outside, so therefore you can never have a 100% perfection in any of the machining. You will always have something off, including the axis that is sharing between the two, the head and the shank, can become off, and that is a little offset you're seeing, yeah. And of course, with our human eye, you can never be able to spot it, yeah. So that's why we have the whole big government organization, which is NIST, doing nothing but the metrology, measuring all of it, yeah. The governing everything that we build got to be within the standard, because if we don't do that or enforce that, all the building will come down, yeah. So you have when the power is in the hands of the people, yeah, people do whatever they want to do. So if you don't check it, they're gonna do whatever they want to do, and your building will come down. Yeah, your bridges will come down, your building will come down, your airplane will come down, your car will break apart if they don't follow the standards. Yeah, so therefore these things need to be, yes, check all the time. And the entire government institution. That's why we need the FBI and CIA to make sure that all of these companies, yeah, are following these standards, which are essential, not to harm the life of the people, the life of the citizen. Yeah. So therefore, even though you're doing the drawing, don't think like this is nothing. It's so important, because there are so many people in the world. Like population is, oh my gosh, just keep going exponentially. Yeah, and you have to build, you have to design, you gotta make all kinds of houses, apartment, you name it. Everybody want a car of their own, so there's hundreds and hundreds of everywhere in each location, yeah, and of where you're living. So your location also is completely categorized by using your address. Yeah, your address is, we call it division, location, market, location on the world where you are located, okay, with your address. So anyway, so and your market items, yeah, everything that we're producing, manufacturing are distributed, and you gotta go and buy whatever you need, of course, right? And all of the major products are your car, your building, your house, your apartment, wherever you're living, and these things are all built, made of all the parts that are manufactured from these factories. So therefore, if you don't follow the tolerances, you're gonna have a lot of issue, and the consumer, that is us, when we use it, we have to put the 100% of our trust to people who are building and building and manufacturing these parts. So therefore, I am totally against those businesses who are reducing the quality of these products. I don't care about the look, but I do care about the function of each of them. The part got to have the standardized tolerance. Otherwise, your function or reliability is gonna go down. So when the reliabilities go down, the life of that product is gonna get disturbed. So the consumer is gonna get more issue using those kind of unqualified or poor quality products. So make sure that it doesn't matter where you're working, you got to pay attention to be able to follow the standards. It's very, very important. Don't do like whatever. And that's why we have to go back, the students, right, and the experience. So people who are working outside a long time with so many years, they still lack the knowledge of it. Okay, they may be skillful doing at one thing, they lack the foundation, okay, or a different aspect or different knowledge, right, relating to whatever they're doing. And I see it like so many times, again and again in many different industries. But then we can't do anything about it because even though what the government, institution, organization trying to do, since the power is in the hand of the people, they don't like whatever they want to do. A different company practicing whatever they want to do. So it's really difficult to deal with everything. The FBI and CIA cannot be able to go into every company either. So we still have the imperfect and chaotic systems in the world, which is totally different from whatever you're supposed to be doing and whatever we have learned from school. It cannot happen in the real life. Okay, so now let's get into the next section, which is your spherical feature control. So the spherical feature control. So the spherical features, features, they can be in relation, to other feature, and of course we're gonna use our positioning, which is your position tolerance. So when we use it, your spherical diameter symbol is going to precede the dimension call out, and is also placed in the tolerance block of the feature control frame. So let's go into here, and you're going to see the special feature control. So that's the spherical object in this diagram. You can see, and it is in relation to the flat, planar surface right there. So let's take a look at it. So you have our data, we have A and B, and they are right here and then right there. You can see our feature control frame with the tolerance, your spherical, your diameter, which is this guy, is 0.6. Don't forget your symbols. So as for the spherical, and that's for the diameter, and that's your size of that, and this is the position. Don't forget which one is what. So position, diameter, that's the size diameter of this spherical shape right there on that part, the feature. And then your datums are right there, datum reference. And of course they're related to this flat thing. Alright, so datum plane, your true position right here of that sphere. And that is a 0.6 diameter, that is where we want to put that sphere in that position, in that part, So we're identifying this. And of course that diameter is the diameter of the sphere. Very different, two different diameter. How big that is, see that? So you can be able to see how small this little thing is, position, So let's come into your RFS. So the center of the spherical element is got to be located on the true position. because it is the center, right? So we'll try to place it. We're going to position it, yeah, as close as possible for the true position. Again, your naked eye cannot be able to spot these variation in this very, very tiny little tolerance zone. Okay, this got to do with the measurement or metrology devices to spot it. All right, so that is going to be measure or verify from these datum reference B and A. Yeah. All right, now let's get into advantages of your position tolerance. So by doing the position tolerancing, so what do we get? So by doing the position tolerant, number one, you have like the Salenduga tolerance zone. We can go all the way up to 57% increase. Yeah, and that will take care of all the maximum error. And then you have like the control tolerance accumulation. That's pretty good. Yes, because we need the tolerance to give space for the error, human error or machining error. And we're going to utilize our bonus and the shift tolerances to again to compensate the errors. Yeah, support the design objective and the intent. Your specification is verified using your fixed gauges. Gauges are always measurement tool that we use to verify. Yeah. What we say, the specifications are like this. Is it true? We're going to use the gauges to verify them. And then, of course, by doing the position tolerance, you get production costs, inspection costs can be reduced. Yeah. So let's do our application guide, which is your position decision. So we'll go into our flow chart. So first, you're going to see if your control applied to the feature size or not. If that is yes, we will go into our axis or center of plane, yeah, location, a dimension, basic dimension. Then we are going to decide if you have the axis or center. Then we will look at the basic location, dimension, originate at your datum. So meaning we look at the axis, yeah, axis or center plane, feature location. Just try to remember like feature location. Second, we're going to look at the datum, location, orientation. Don't forget you're dealing with your position, not the size of it, not the size of your feature. Yeah. So then we will look at the datum reference. Yeah, where do we measure from? Verify from. And then if you have it, then we will go into our maximum material condition or least material condition, your modifiers. Then after the modifiers, if we have all of this, yes, then you have your acceptable application of that position tolerance. And of course, this is your RFS, which is regardless of feature size, control. Then the second control is if you're not doing the feature size, then you must be doing the feature. So if you're doing the feature, then you can do the position, tolerance. So therefore, that's unacceptable. Then okay, now we're gonna go back to if your control is on the feature or size, and if you have the axis or center and you don't have it, then it is not acceptable because you need the axis or center, to locate or to position or do the placement. That's what it say. And then after that, we're gonna take a look at our basic location, and if you don't have it, unacceptable. Then we will look at the next step, datum. If you don't have it, unacceptable for position, control. If you don't have your modifier, again, it is unacceptable. Now we're going to put them all together for this decision flow chart, and you're going to go each one of them this way. We have acceptable, and the other one, the other condition is your unacceptable. Sorry, I don't have time to bleach these blue stuff. It's still there. Okay. And then the next is with your position tolerance with the maximum or least material condition. So how do we decide that? First, we're going to look at the feature of site. Then we're going to look at the feature location with the basic dimension. Then we're going to look at the basic location dimension originate from the datum or not. And then we're going to look at the datum reference, right, used in that feature control, the same thing. And then we'll look at the modifier. And if the modifier is there, we're going to accept. So it's about the same as your first position, even though we're looking at the max material condition or your least material condition. And the next one, of course, will come without the feature size. So the control is not on feature, we can do that, and acceptable. Then if the control is back to feature size, then we're going to take a look at the feature location. If you don't have it, and acceptable. Then we look at the basic dimension. originating at the datum also unacceptable. Yeah. Then we'll look at the datum, the same thing. If you don't have it, unacceptable for this. Yeah. So which is completely the same as the previous flow chart for decision. Then we're going to look at if the control is regardless of the feature size, and if you don't have a no modifier, then it is unacceptable. Then we're going to put them all together, and it doesn't really change that much. Yeah. So when you go back to the very first decision making, you're going to see the differences there isn't. Okay, they're all the same. So here, that's regardless of feature size, and then yes, and this one, okay, is going to be the maximum least. Yeah. All right, now let's go into the same decision making apply. Yeah, because you don't change, doesn't matter what that is, you're still in the position anyway. Yeah. And don't forget, you can go back, to check your yes or no stuff, and make sure you go slow. Don't go fast like I do. So when you're taking it in for the first time, you gotta go very, very slowly to get it, and you have to repeat it many times for you to be able to get it. We are designing the tests because I know that everybody is struggling with the time, so they can't be able to digest the material until they get it, to retain it in the brain. So we still give you like 2 chances for the quiz, right? Trying to give you about 60%, right, open book. So that way you at least get the passing grade for a very difficult subject like that. Yeah. So we're fair, for equity stuff. All right. So let's go into here. Okay. Now let's wrap it up for the location. So we have position, and then of course we go this your concentricity and your symmetry. So your position is really heavy, a lot of different stuff in there. So summary, we're gonna summarize the location controls for this 3 tolerance. So one location tolerance. So right now for position tolerance, your location, all right, tolerance is going to apply only to the feature of size. Okay, your rule number 1 is going to be overwritten, and then your virtual condition is going to get affected, all right, for position tolerance. Modifiers are applicable, and we use it anyway in case where position is applied. So that's your rule number 1. And then your datum reference is always required in your feature control frame, because without the datum reference, verification cannot happen. Yes, so make sure you study the rules. Okay, rule number 1. And of course your modifier, that I shouldn't use a rule here. Let's just use the rule number 1 here. This is just differentiating between this condition and that. Here is modifiers applicable, but for this case, for the concentricity and symmetry, your modifiers are not applicable. That's your second scenario right there. So which is legend is right here. Number 1 little triangle right there. So that's telling you the modifiers of the maximum and least material condition may be used with position tolerances. And then the second one is here, your concentricity and your symmetry of all of your features right on your part are always apply, regardless of your feature size, your RFS. So make sure you know that 2 difference. Right now, your RFS, your rules, everything is gonna like confuse you. But as you read again and again, you will clearly see it. Yes. So make sure you study. So right now, let's get into concentricity and symmetry. So of course, we will first look at the location tolerance, whether that's applied to the feature side or not. Yes, it is. For these location tolerances, and then your rule number 1 again override, and then your VC, your virtual condition, is also get affected for these location tolerances. The only difference is right here, modifiers, we don't use it for concentricity and your symmetry. In cases where your concentricity and symmetry are applied for location. So and then we go the same thing, your datum reference is totally needed for your feature control frame. All right, in that feature control frame, to control these location tolerances. All right, so let's go into the exercise. So your job, my job is finished, and your job is to do your problem number 71 in your textbook all the way to 77. Of course, I ask you your minimum assignment, 3 of them, yeah? So choose 3 of them, do it, do not copy. I give you the answer to study with it, not to copy it and turn in and back my own answer right in there. Don't do that, okay? Some students are doing it. I need you to study with it so you can go back and check your understanding is going to be okay or not, and make sure you study 71 all the way, because the final exam question is going to come, yeah? No, this is test 3, sorry. So the test 3 questions are going to come, yeah, out of this. You know what to study, and I mean, there's nothing here to study. 71 or 77 is how many questions are there? 1, 2, 3, 4, 5, and then 6, and then 7 questions right there. And you can't be able to do it, so I don't know what to say. Okay, 7 questions for chapter, what is this chapter? Chapter 9, yeah? So test 3, make sure you study chapter 7 and chapter 8, and then chapter 9. What am I going to ask you? I am going to ask you the exact same problem out of these problems that we do, okay, your homework. The answers are given to you there. Your job is only to study, and I have to deal with a couple of the students who are not doing it, yeah? And I don't know what is going on in your life either, and I have no idea why you can't study at all. So I don't want to scold again and again for that, yeah? It's getting me. Now we're in the test 3. So make sure you please study, yeah? Make sure you study all of that. Okay, so let's end it right here for the part 3.